Hi, everybody. Welcome back to Unit 1 for AP Physics C Mechanics. So topic 1.2 is displacement, velocity, and acceleration. All right, so let me just preface by saying if you've taken a mechanics course, this is, most of this slide is going to be repetitive, right? The concepts don't change, right? Displacement is what it is, velocity is what it is, acceleration is what it is. However, in an algebra-based course, we always assume that this is constant, right? In Physics C, in a calculus-based course, this is acceleration may or may not be constant. So you have to use calculus to come into play here. All right, and I do apologize for how small this is, right? Because I wanted to make sure we get all this on one slide. So when using the object model, size, shape, and internal configuration are ignored. So that just means if we have a car, right, we're ignoring all the moving parts of the car. The car is the object, okay? Same thing like if it was a ball. We're just worrying about like the ball, and anything associated with the ball is an object, okay? So displacement, if you remember from an algebra-based course, is simply a change in object's position, okay? Where you're going to do, if you want to remind yourself, this is your first official equation. Delta x is our displacement notation, and it's going to be x minus xo, so final minus initial. And then what we do is averages of velocity and acceleration are considered calculated considering the final states, the initial and final states over an interval of time. So average velocity is changing position with respect to time. And then average acceleration is changing velocity with respect to time. Okay, and we're going to talk about graphing, but remember, this is the slope of an xt graph, and this is the slope of a vt graph. Okay, we're going to get into that here in a little bit. Now, so here's where we get different, right? And so as the time interval used to calculate approaches zero, those average velocities or average values now become something known as instantaneous. So that means at a particular moment. And this is where we introduce in calculus, okay? So we think of velocity is the derivative of position, okay? And acceleration is the derivative of velocity. And so what does that mean? So if I have a function, right, let's say I have a position time graph, right? My averages will be like from here to here, right? From 0 to T1, okay? So that would produce an average. So it's like if I took those 2 points, connected them, and I got a slope there by using my, delta x over delta y. Now, the instantaneous velocity would be, okay, I want to find the velocity at T2, okay? So I take those 2 points and I start shrinking the distance between my my 0 or my 2 points, my time interval, to where now it's 0. Now I have a tangent line. And this is what we're finding the slope of, is this tangent line. I didn't mean to draw like a slope notation thing there. Okay. And that's where all right. So when we talk about instantaneous, we're taking the derivative. Okay. And if you go back and look at the channel, there's some basic calculus information, especially if you're taking this, beginning of the year. In my classes or in class, we start with electricity and magnetism. So they've already had some information with the derivatives. And in fact, day 1, I'm doing introduction to calculus. Okay. And so time-dependent functions and instantaneous values of position, velocity, and acceleration can be determined by 2 things. Differentiation, which is what we have here, right? So using that D notation as differentiation. And then we can also use it for integration. So an example would be, so the way you think about it is integrals are the antiderivative or the opposite of a derivative. So if I'm want to find position, right, or delta x, I kind of separate, multiply this by dt on both sides. right? And so I end up with dx equals v dt. Now to get rid of the differential, right, the d notation, I take the derivative. Okay, so I end up canceling the d on the left side, and then it becomes v dt. But when you do integrals, you're going to end up with like a plus c, which in physics is essentially our initial velocity. For you to determine that, they would have to give you initial conditions. You know, at t equals 0, x was this. At t equals, or sorry, this is not x0 or v0. This is x0. Okay, at t equals 0, x was, you know, the object was here. At t equals 0, its its velocity was this. And that'll help you determine this. In fact, in the example problem, we do that. Okay, so speaking of the example problem, let's do it. All right, so we have a particle moving along the x-axis with an acceleration of a equal to 18t, where it has units of meters per second squared. If the particle at time t equals 0 is at the origin with a velocity of negative 12 meters per second, what is its position at 4 seconds? Okay, so we're going to start with our acceleration function. We know that acceleration is dv dt. So I do the same thing like I showed you in the previous slide with, okay, I multiply both sides by dt, right, and I end up with dv equals adt. To get rid of it, I take the integral, and so I got v equals the integral of adt plus initial velocity. Okay, so what I need to do is take the integral. So if I want to find v, I do the integral of 18t dt. Okay, the rule is you plus 1, so 1 plus 1, right? So we're going to go v equals 18t squared over 1 plus 1, right? So the basic power rule. So it ends up being 2 plus c. That c is the constant that we need to determine to figure out what v0 is. So that we end up with 9t squared plus c v of t. But they tell us at t equals 0, it's already moving negative 12 meters per second. So what does that mean? At v0, so when time is equal to 0, it is moving at negative 12. Okay, oh, sorry. I wrote that in the wrong spot. Boom. So this should be our plus c. And we know that equals negative 12, right? And so that goes away. And they just tell us that c equals negative 12. Well, that's our initial velocity. So our velocity function with respect to time is 9t squared minus 12. Now I need to figure out the position function, right? So what is x of t? Well, we talked about it on the previous slide. It's the integral of v dt plus our xo, right? Our initial position. So I take this function, plug it in there. So x of t equals the integral of 9t squared minus 12 dt. Okay, so again, the rule is plus 1 over plus 1. So plus 1 over 1 plus 1. Well, this is t to the 0, so plus 1 over 0 plus 1. And so I end up with x of t equals 9t cubed over 2 minus 12t plus c. Okay, oh, sorry, this should be 2. So it should be over 3, not 2. Well, that becomes 3. So x of t, the final function, becomes 3t cubed minus 12t plus c. But I know at t equals 0, it's at the origin. And so I take our function. So x of 0 is equal to, let's just call this 0. So 0 equals 3 times 0 cubed minus 12 times 0 plus c. Well, that makes our c equal to 0. And so now we have our position function. So x of t equals 3t cubed minus 12t. Now, I get it. It's a lot of work to get to this function, but that's what happens. And the AP will kind of stack the questions. So now I need to figure out where is it at 4 seconds. So now it just becomes 3 times 4 cubed minus 12 times 4. Okay, and we end up at a position of 144 meters. Okay, even though it starts moving, with a negative velocity at some point in time, right? This acceleration has caused it to stop and move the other direction. Okay, so that's the position or displacement velocity acceleration topic. In the next video, we're going to talk about different ways to represent motion.